Hello and welcome to my new video on 3D modeling. This time we will learn how to generate 3D Cartesian distributions. Why do you need them? Most often you need a Cartesian distribution to generate background settings. A seemingly random distribution of things, erythrocytes in this case. Using a few loops, it is pretty easy to do this. This is a Cartesian distribution in a 2D version, in the xy plane. In a strict sense, it is only called Cartesian when all three or two axes are arranged with right angles towards each other. In principle, we also could create all kinds of distorted systems, but usually we stick to the plain Cartesian system. How do we create such systems? Let's start with the first dimension. For positioning these spheres, we only need one loop, which will simply add the distance in one x direction to the previous position and place a sphere on the new position. Prior to this loop, we have to define the number of elements in x direction and the distance between elements in this direction. I have already included the numbers and distances of elements in y and z direction in this script. We will need them later. As our next step, we define a loop working through all elements in the y direction and including an x loop for each of these elements, the y loop. At the end of this loop, the x loop has to be reset to 0 to be able to start this loop again for the next y element. At the beginning of the y loop, the y coordinate is calculated in a very similar way as the x coordinate in the x loop. To go one dimension further and obtain a 3D distribution, we have to use a third loop, which will calculate elements in the z direction, the z loop. For each of these elements, nested y and z loops are done, defining a complete plane in every case. Well, that's all. We could stop here. But since this 3D arrangement looks pretty boring, I will show you some possibilities how to make it look more interesting. For this, we will focus on two dimensions for a start. One possibility to modify our distribution is to shift every second x row by half a distance. X row meaning a row along the x-axis corresponding to one common y coordinate. This way, subsequent x rows become staggered. If you look closely at this distribution of elements, it is not perfect yet because the triangles defined by adjacent elements have sides of different lengths. To obtain equilateral triangles, we have to decrease the distance between subsequent x rows, the distance between y elements, by the factor of square root of 3 divided by 2, 0.886. By doing this, we obtain a distribution composed of equilateral triangles or hexagons. Another thing we can do with our distribution is to add some randomness. First, let's simply add some randomness to the positions just calculated. In this distribution, I limited randomness to 20% of the distance between elements. In a similar way, you might do an animation showing the random thermic movement of atoms from a crystal. When adding randomness accounting for 90% of the distance between elements, our pattern is almost lost. Nevertheless, the resulting pattern is not completely random. It rather represents a pretty even distribution of things looking like random. This here is a real random distribution. Each element is, independently of all other elements, distributed over the whole area available. As you can see, random voids are much more common here when compared to the previous distribution. The last thing I want to show you is the 3D version of such a random distribution. Every element here is randomly distributed over the whole volume. The result resembles something like a cloud. Now for a background, you can either use this random cloud or the more ordered version introduced above with fixed positions and a certain degree of randomness added. Here I'm showing you a few backgrounds generated this way. Let's start with influenza virus particles. Transparent in the foreground and is transparent in the back. The use of different surfaces for the same thing may be somewhat confusing. So better use the same texture for foreground and background. These are meant to be influenza viruses above some mucous membrane. These are some streptococci I visualized here. Problem is here that elements from the foreground and background are too similar to each other. In this streptococci image, this looks better. Here you can clearly distinguish foreground from background. So this was it for today. I hope you enjoyed it. Stay tuned for some spherical distributions in my next 3D video.